Hello everyone, I am Saleh, a PhD candidate at UNSW Sydney. I am delighted and honored to present my research at the Rilem Youth Pacific webinar platform. So welcome to today's presentation on industrial byproduct based low carbon seawater and sea sand ultra high performance concrete. First of all, I would like to acknowledge the ARC Discovery Grant jointly awarded to my supervisor, Professor Xiao Lin. And this is our team working across different universities in Australia, Hong Kong, and China. There are several main topics covered within this discovery project. However, for today's presentation, I will be focusing on one of the two topics that I am covering within my PhD. So, we all know that overproduction and overuse of OPC concrete can lead to scarcity of natural resources such as fine aggregates, freshwater, natural coarse aggregates, and also can be a significant source of carbon dioxide emission. Global cement production in 2021 all over the world was 4.4 billion metric tons, which was more than 4 times than it was in 1995. At the same time, industrial byproducts such as slag and silica fume are hazardous in nature and they need to be managed properly. Different literatures have established seawater and sea sand concrete as a promising alternative to conventional concrete. In my PhD, I am trying to incorporate marine resources in ultra high performance concrete production. This means seawater will replace freshwater, sea sand will replace river sand, and OPC will be partially replaced by slag and silica. So the aims of this research are to develop a proper mix of industrial byproduct based low carbon ultra high performance seawater sea sand concrete, which will have the desired physical, mechanical, transport and durability, and also chloride binding properties. And in the second part, I will be trying to incorporate this special type of concrete into FRP based hybrid and composite structures, and will be evaluating the combined influence of long-term loading and harsh marine exposure conditions to these type of structures. However, for this presentation, I will only be focusing on the first aim of my PhD research. So, we have developed several mixes in the lab, the parameters being replacement of OPC up to 62.5% by slag and silica fume, different sources of aggregate, and water to binder ratio. However, to keep things simpler, in this presentation, we will only evaluate 4 mixes. 3 of them are seawater sea sand ultra high performance concrete. Number 1, 100% OPC based control mix. Number 2, OPC and slag based binary mix. Number 3, OPC slag silica fume based trinary mix. And for comparison purposes, we will also discuss one conventional ultra high performance mix that is developed from natural water and natural river sand. So these are some photos that shows our mix design, mixing procedure, batching and testing of ultra high performance seawater sea sand concrete in the CIES lab of UNSW. Now the effects on the compressive strength. We have found that addition of SCMs can significantly lower the early age strength up to 3 days. However, after 28 days and beyond, the long-term strength will surpass the control strength. This is primarily because of the high pozzolanic reactivity nature of silica fume and its filler effect, which will improve the particle packing density. When seawater was used in mixing, it had a positive effect, especially in the early age. However, when the concrete specimens were exposed to seawater for a long time, it had some negative effect. This is because the high chloride content in seawater can accelerate the hydration reaction, especially in the early age of concrete. It can block the concrete pores and increases the initial strength gain. However, when concrete is exposed to seawater for a long time, expansive and leachable components form, and also it can create micro cracks on the concrete which can deteriorate the compressive strengths over the long term. To complement our mechanical test, we performed heat of hydration test and found that seawater indeed accelerates the cement hydration. Use of seawater not only increases the heat flow but also acceleration peak has been shifted by 6 to 8 hours, which is an indication that seawater accelerates the pozzolanic reaction. At the same time, use of over 50% SCM can significantly increase the cumulative heat, especially because of the filler effect and production of extra nucleation sites. However, it was interesting to see that the seawater generated mixes produced more heat in between 12 to 30 hours. However, after 72 hours, the seawater mixed concrete produced lesser heat compared to the controlled tap water based mix, which indicates that the early age strength improvement of seawater and the later age strength decrease by using seawater. Next, moving on to the transportation properties, we have found that the effects of SCMs were prominent in water absorption and volume of permeable void tests. As SCMs produce more CSH, which means more refinement to the pore structure. However, it was also found that use of only slag does not significantly enhance the transport properties, probably because of their slower pozzolanic reactions. When marine UHPC was compared to conventional UHPC, we found that marine UHPC generated superior transport properties at earlier age, however slightly inferior after long term, which is because the calcium chloride present in seawater can accelerate the early age hydration, and after long term exposure in seawater, it can reduce the polymerization of CSH and thereby degrading the transportation properties. Also, the AFM phases within the concrete can bind with the free chloride and form Friedel salt, which can physically block the pores, which we will discuss in details later. We performed a non-destructive test of electrical resistivity and found that the ternary mixes, the OPC slag silica fume based mixes, produces significantly higher electrical resistivity compared to control. When compared to conventional UHPC, the marine UHPC produces considerably higher electrical resistivity. We evaluated the resistivity per megapascal compressive strength and found that 50% substitution of OPC by SCM in marine UHPC produces the highest resistivity per megapascal compressive strength, which means this is the most durable concrete with comparable mechanical properties. Now, an important part for a marine concrete will be the chloride migration into it, and we found that the utilization of slag and silica fume in the ternary marine UHPC significantly improves the chloride penetration resistance. When compared to conventional UHPC, the chloride penetration resistance of marine UHPC is much higher compared to the conventional concrete. We can also see this from the rapid chloride migration test that almost 3/4 of the depth has been penetrated by chloride in the control mix, whereas in the 50% SCM based trinary mix we barely can see any chloride front. Now, moving on to chloride binding, we know that the chloride in concrete can be bound in two major ways. One is the chemical binding by formation of Friedel salt. Another one is the physical adsorption within the hydration products. Now, in our concrete, we have two types of chloride. One is already available from the mixing seawater and sea sand, that is called the internally available chloride. We found that internal chloride binding capacity was highest in the OPC slag binary mix, followed by the control mix, and the binding capacity was lowest in the silica fume base ternary mix, which is corroborated by literature because literature suggests slag can increase the chloride binding capacity. However, inclusion of silica fume can significantly decrease the chloride binding. But as the silica fume can produce more secondary CSH, there is a chance that the physical binding can improve. So we evaluated the chloride profiles of all types of mixes and found that marine UHPC and conventional UHPC provides very similar and comparable chloride profile, and the binding capacities of the external chloride from the marine environment exposure fall within a very narrow range of 30 to 36% for all the types of mixes, which means although we used silica fume, it did not reduce the external chloride binding capacity significantly, which makes us think that the physical binding govern within the microstructure in our mixes. From the microstructural characterization, we found that the 50% SCM based ternary mix produces a much more compact microstructure without any visible pores compared to the control. We could see abundance of CSH gels, and also the unhydrated binder particles were abundant within the microstructure. From XRD analysis, we found that the Portlandite has significantly reduced in the ternary mixes compared to control, and we also saw that the monocarboaluminates in the OPC slag based mix was diminished, and this is the reason why adding only slag will not provide a significant improvement in the transport properties, and this also emphasizes the importance of adding silica fume in this type of marine ultra high performance concrete. We detected Friedel salt, however the peaks were not prominent, and from the EDS mapping, in some rare instances we located the regions rich in Friedel salt. We came to a conclusion that as the water to binder ratio is very less, so the available water and thus the available chloride for chemical binding is also significantly less, which indicates that the physical binding of the chloride has governed in this type of concrete. Now we come to the carbon footprint intensity and saw that utilizing supplementary cementitious materials can significantly reduce the carbon footprint. The carbon footprint intensity in the marine UHPC can be as much as 25% lesser than the conventional UHPC, mainly because of the absence of the steel fibers. We do not have any steel fibers in our mix to avoid the corrosion chances. Now when we compare the carbon intensity to produce per megapascal concrete strength, we saw some impressive results that with the utilization of SCMs, the carbon footprint per megapascal of strength will reduce. If we compare the carbon footprint per unit durability, the results are amazing. We can see that the trinary mixes can save up to 90% of carbon dioxide production compared to the control mix, and 40 to 75% less carbon footprint intensity compared to the conventional UHPC mix. So in conclusion, we can see that the industrial byproduct based SCMs can improve the mechanical properties slightly, but it can significantly enhance the transport and durability properties. Friedel salt can densify the microstructure by partially blocking the capillary pores. Internal chloride binding is not significantly affected by the SCMs, and in terms of external chloride binding, the marine UHPC and conventional UHPC are very similar. Also, physical chloride binding seem to govern. Monocarboaluminate depletes and thus compromises the slag's pore refinement capability. Also, in terms of carbon footprint intensity, marine UHPC is a lot better than conventional UHPC. So we can say that marine UHPC can be a durable alternative, low carbon alternative compared to conventional UHPC. These are the publications from this part of the project. If you are interested, you can have a read. I would like to acknowledge again the ARC Discovery Grant, Randwick Council, Mark Wainwright Analytical Center, and special thanks goes to my supervisors and our collaborators. So that's all from me. If you have any questions, feel free to reach out. See you again.